Okay, I think you can see what I've written in yellow over here. Okay, now remember our function f, capital F, was the gradient of little f. The integral of our big F function dot ds from 0, 0, 0 to 1, 1, 1 turned out to be 1. Now, I haven't shown it, but had we used a different path from 0, 0, 0 to 1, 1, 1, we would have still gotten the same result. That's because the big F function is the gradient of some other function, some scalar function. Okay? Anytime this function is a gradient of a scalar function, the integral between 2 points is path independent. Doesn't depend on how you get from one point to the other, as long as you stay inside the domain of the function. Okay, so we can say that delta f, this is not to be confused with del f, delta f, the change in f from 0, 0, 0 to 1, 1, 1 is 1. And again, the line integral of your gradient function, big F dot ds from here to here was 1. That's generally the case. The line integral from one point to another is equal to the change in the value of the potential function, the source function little f, from one point to the next. Evaluate the little f function, x squared, y squared, z squared, you see it over here. Evaluate that function at 0, 0, 0, you get 0. Evaluate it at 1, 1, 1, you get 1. What's the change from here to here? From 0 to 1, change is 1. Okay, then the integral of f dot delta s, line integral, from 0, 0, 0 to 1, 0, 0, and that's the line integral along the broken line path from the origin to the 1, 1, 1 point and then back to the 1, 0, 0 point. If we do the integral along that path, the change is what? The change is 0. Well, what's the change in our f function, our little f function? Well, at 0, 0, 0, this function is 0. At 1, 0, 0, again, it's 0. And we already saw that. We already alluded to that. So, in a sense, this function little f is an antiderivative of its gradient. Because what's an antiderivative? If you're integrating something in one dimension, the antiderivative is going to, a definite integral, the antiderivative is going to be evaluated at the upper limit and at the lower limit, and you're going to subtract the result you get at the lower limit from the upper limit. What's that give you? That just gives you the change in the value of the antiderivative. So your definite integral is just the change in the value of the antiderivative from your lower limit to your upper limit. Well, here, the integral of the gradient function, the big F function in this case, the integral of your gradient function turns out to be equal to the change in your little f function. So your little f function is in the same sense acting as an antiderivative. This is a very, very important idea. And one other word that we want to put in on this. I'll just write the word because you're going to see the definition. Yeah, bad circle there, I kind of bumped into the board. This big F function is what we call a conservative function. A conservative function is a function that has this property. It's the gradient of some scalar function. And sometimes that scalar function is called a potential function. And then your vector field function is called, well, it's the gradient of your potential function.